Okay, good morning, everybody, and it's a great pleasure to be here. Thanks a lot to the organizers. So I suggested to give a tutorial talk, and I would like to give more like a pedagogical, educational talk, not focused on our recent results, but to provide a picture, big picture of momentum and angular momentum properties of structured waves. So please do interrupt me during the talk if there are any questions. It will just help me to see the reaction of the audience. Okay, and so this presentation is inspired by my recent review. Will appear soon in a journal called Contemporary Physics. It's a nice review journal with an excellent editorial board, and they commission reviews on some interesting topics, which about 20 pages long, and which should be educational and suitable for graduate students and so on. So I recently worked on this, and there I described kind of unified picture of momentum and angular momentum properties of different classical waves, including electromagnetic waves, sound waves, elastic waves, waves in isotropic plasma, and finally water waves. I will not discuss all these examples today, only the most important. And here is the outline. So I will start with the introduction of the main notions. And then I will suggest a field theory approach to describing momentum and angular momentum properties of waves, which should work in all these cases, and then consider specific examples of electromagnetic waves and sound waves. And finally, I will show very clear visual demonstrations with water waves, and also describe manipulations of particles with structured waves. Okay, let's start with the introduction. And it's well known that the story of wave momentum starts with Kepler's observation that comets' tails is always directed away from the sun, and then Kepler suggested that this is due to some solar wind, solar radiation, which pushes a pressure on the comet's tail. And this is indeed so, at least partially. And so electromagnetic radiation momentum is responsible for this direction of the comet's tail. And another milestone result, which determines our understanding of wave momentum, is the Broglie relation from quantum mechanics, that momentum is proportional to the wave vector of any propagating wave. Okay. Then another example is completely classical. In the middle of 19th century, Stokes noticed that he calculated that water surface particles in a water surface wave, they not only oscillate or move around the circles, but also drift in the direction of wave propagation. And this drift is known as the Stokes drift, and it's also a signature of the momentum carried by this propagating water wave. Okay. Then the first example of angular momentum of a wave was found. It's commonly believed by Poynting, who noticed that in 1909, who noticed that a circularly polarized light can carry some angular momentum, and he noticed it by calculating the transmission of circular polarized light through an anisotropic plate and some torque exerted on this plate. And according to the, it's difficult to handle this pointer, to quantum mechanical picture of photons, this is spin angular momentum of a photon. It's proportional to the helicity or degree of circular polarization, and is given by this expression for one photon. So it's again directed along the k vector and involves h bar. But it's less known that exactly the same result as in the paper by Poynting was reported by Sadowski 10 years before Poynting. And this is an example of let me, okay, of a very nice paper, but published in an obscure journal, which was totally missed and forgotten. Unfortunately, this was a publication in the journal of Yuriev University, which was a Russian empire then, and now it's Tartu in Estonia, so it's Tartu University, well known. Unfortunately, on their website, there is a scanned copy of that old paper. It's in Russian, but we translated it more, the main results are translated in our recent review on optical forces and torques. But here is the idea, quotation from this paper. The forces developed during the transmission of circular polarized electromagnetic waves through a crystal plate tend to lead it into continuous rotation in the direction of rotation of the electromagnetic forces, means fields, in the incident waves. And the largest torque is obtained for the 2/4, means half wavelength plate, which transforms right-hand circular polarization into left-hand circular polarization, so it exerts maximum angular momentum exchange and torque. Okay, and all predictions of this paper were observed only 100 years later in this Nature paper by Friese. The very first experiment on angular momentum of circular polarized light was by Bett in 1935, but all torques were observed in this Nature paper, and this is results from it. This was a microparticle of calcite, I guess, some birefringent material, and in the circular polarized light, it experienced torque and rotated in the direction of circular polarization. Okay. Then the next quantity we will discuss is the orbital angular momentum, which can be present in any waves, not only electromagnetic. And it's produced by circulation of the local momentum density, or we can say azimuthal phase gradient. The usual momentum is associated, it's very difficult to use this pointer, is associated with the phase gradient here. And if the phase goes, depends on azimuthal coordinate. Can I have just a pen? Azimuthal coordinate, so it has this dependence. Then we have gradient of this phase, which is proportional to the number L, which is topological charge of a vortex, as we know. So the orbital angular momentum is, in quantum mechanical terms, is given by h bar L per 1 photon. Okay, and it's actually, this phase gradient is R cross momentum density, because momentum density azimuthal component is given by this form, and we need to multiply it by R to get the angular momentum. Okay. Here is an example. The simplest Bessel solution of Bessel vortex solution of Helmholtz equation in 2 dimensions. It can be considered as a superposition of waves propagating in all directions and having an azimuthal phase. This one. Okay. Okay, excellent. Thank you. Okay, so this results in this equation, Bessel function of the radial component and the usual vortex phase. And this is how it looks like. Intensity, brightness is proportional to the intensity, and color proportional to the phase. And here is the result of particle manipulated by such a Bessel vortex beam, experiment from 2003. So particle is trapped in the maximal intensity area, and then it orbits due to the orbital angular momentum. Actually, it's the same radiation pressure like the one which pushes comet's tail, but now it's directed in the azimuthal direction. Okay. Again, some historical remarks. As we all know, the modern development of optical angular momentum started from this Les Allen paper in PhysRef-A, 1992, and it's the most cited paper in PhysRef-A for all times. 12,000 citations by now. And the same year was published a paper, Rotating Waves, in American Journal of Physics. It's not Russian Empire. It's a journal in the USA, available, modern. It actually was submitted half a year before this Les Allen paper. And it reports all the generic results for vortex waves, angular momentum. As you can see, there is a solution for Bessel modes and angular momentum m, and this is h bar per quasi-particle. And separately recognize that this is not only property of optical waves, but any kind of waves, including some examples for water surface waves. But till now, it has only 39 citations. And we were not aware of this paper. We just recently made a work on water surface wave vortices. And first we published theory in PRL. And then this year, experiment in Nature. There are more results than only just generation of vortices. But nevertheless, and a referee of our Nature paper pointed to this old paper by separately to us. Otherwise, it's completely like forgotten. Anyway, the results which were envisaged by separately were fully described only in 2024 and realized in this year experimentally. Let me see. Yeah, here we generate vortices in a water tank from 24 sources with phase delays. And this is where all sources are in phase, which generate zero order mode. It's not a vortex. We have maximum amplitude in the center. And this is vortex L equal 1 mode. We have one maximum of center, which is rotating. Then L equal 2, two maxima rotating. It's exactly the Bessel mode. And then, for example, L equal 8 with 8 azimuthal maxima rotating in the direction of propagation. Okay, so let me proceed with theory now. We need some good theoretical approach to describe all these momentum, spin, and angular momentum properties. And we start with, let me see, with a just generic vector field, vector wave field, F depending on R on coordinates. Let it be some medium. So this vector field describes displacement of the medium particles, for instance, some inhomogeneous wave field at a given moment of time. And then all these particles oscillate, right? And if we consider translation of this wave field by some small vector d, we can decompose in a Taylor series and put this into exponent. And then we see that this operator is the generator of translations, or in quantum mechanics, this is canonical momentum operator, minus I gradient. It generates translations of the field. OK, this is simple. Now, if we would like to consider rotations of the field, it becomes a more complicated story. Have the same field, and we need to rotate it in space by small angle d, for example, about the z-axis. It might seem that we just need to apply the rotational operator, but it's not sufficient because it's a vector field which is characterized by the direction in every point, but also by the field distribution between different points, like amplitude and phases and so on. And to rotate both direction or polarization in every point and field distribution globally, we need to apply the rotation operator twice. First time to the direction of the field here, and second time in the argument to the distribution. And it should be r minus 1, the inverse operator. And when we expand this in Taylor series, we have two terms for the rotation. And here how it looks like. If this is we rotate only distribution, and this we rotate both distribution and direction in every point. and which provides perfect rotation of the whole picture. And then this Taylor series, again, could be put into exponent. And the exponent, we have a generator of rotation, which is total angular momentum operator. And it has two terms. The first term is just R cross momentum operator, which is minus I gradient. And the second term is the spin operator. And for example, Z component of the orbital angular momentum is just a derivative with respect to phi in polar coordinates. And the Z component of the spin operator looks like this. So it's like spin 1 matrices known from quantum electrodynamics and so on. In fact, these are generators of SO3 rotations for vectors in space. And what is important, this angular momentum operator, again, it can be found in textbooks on quantum electrodynamics. But it's valid actually for any vector fields, for any classical vector fields. Sound waves, elastic waves, water waves, doesn't matter. It's just a rotation of three-dimensional vectors. Okay? Oops. What happened? Okay. Now let us determine the momentum and angular momentum densities in a monochromatic wave field. And we will use complex representation of the field and also the real field, which is time-dependent, like this. So we can write Lagrangian density of a wave field, and let us suppose that it has such a form with the kinetic term, kinetic energy term, which is given by time derivative of this field, minus some potential energy term, which depends on gradients of the field. And we will see that this is the case for most of classical waves. And so we apply Noether's theorem. If the Lagrangian, which is integral of this, is invariant with respect to translations and rotations, then this results in conservation of the momentum and angular momentum of the field. And we can write momentum density and angular momentum density for this wave field. And it's, again, general equations from Noether's theorem. Momentum density is now given by this F dot grad F form. And total angular momentum, again, has two terms. The first one is the orbital, R cross P, as it should be. And the second one is the spin part. And you can see that the orbital angular momentum density is always extrinsic, which means that it depends on the choice of the coordinate origin. So if we shift the coordinate origin, we change the orbital angular momentum. It's not a like uniquely defined quantity. But spin density is intrinsic. It doesn't depend on the choice of the origin. It doesn't involve R explicitly. Okay? So in principle, if we are talking about densities, it's sufficient to characterize wave by momentum density and spin density. And the orbital angular momentum is just a derivative of the momentum density. Okay? Okay, so in monochromatic field, we can type average this momentum density, and it provides this standard form, imaginary part F star grad F, which is similar to the probability current in quantum mechanics. And essentially, it's a gradient of the phase of each component multiplied by the intensity of each field component and summarized sum over all components. So here is an example of just one component of the field, phase and intensity distribution, and momentum density is just the gradient of this phase. In some points it has forms vortices and so on. Again, OM density is R cross momentum density. But nonetheless, it's important to point out that although the orbital angular momentum density is purely extrinsic, the integral orbital angular momentum for vortex modes can be intrinsic. And let me prove this. So let us make a shift of the coordinate origin by some vector d, and orbital angular momentum density is shifted, and therefore by choice we can, for example, vanish this OAM density in any point. But if we calculate the integral value of OAM, then it transforms like this. And this shift is makes vector product with the total momentum of this field. And in particular, if the total momentum vanishes, like for two-dimensional vortices, the integral angular momentum becomes invariant. Or if we consider a component of the angular momentum along the mean momentum of the field, this component is always invariant with respect to translations. Okay? And for example, this is the case for vortex beams. So this is a vortex beam field, some radial amplitude, radial dependent amplitude, some vortex phase, and z propagation factor. And it's easy to see that integral momentum is directed along the z axis of the propagation, and the integral orbital angular momentum is also directed along the z-axis of propagation. And this component is invariant with respect to any translations of coordinates. This was first noticed by Michael Berry in 1998. Okay. Then about the spin density. So time average spin density is given by this form, F star cross F, an imaginary part. And it's easy to see that this is related to the polarization ellipse of this field, because again, for any vector field, not only for optical monochromatic wave field, the vector of field traces an ellipse in three-dimensional space, and this is polarization ellipse. And spin is just the cross product of real part of F and imaginary part of F, that is of major and minor semi-axis of this polarization ellipse. So it's proportional to the area of polarization ellipse, and it is normal to it. And for arbitrary structured wave, like here, just superposition of many plane waves, we can have arbitrary three-dimensional polarization textures and spin density textures. Okay. Now let's continue with explicit examples for known wave fields. First, electromagnetic waves. As we know, these are transverse waves existing in the vacuum. And these are typically described by electric and magnetic fields, but for our purposes, it's convenient to introduce a vector potential in Weyl gauge, for example, where the electric field is just time derivative of A, and H is just the curl of A. And then the electromagnetic field Lagrangian is given by this form, exactly as we suggested. Kinetic term is the electric energy density, and potential term is the magnetic energy density. We can derive Maxwell's equations of motion, and we use just our general equations from field theory to write the electromagnetic momentum density and spin density involving complex electric fields, and having this factor, I use Gaussian units for simplicity. Okay. And for a plane electromagnetic wave with circular polarization, we have this electric field dependence. So momentum is proportional to k and directed along the z-axis. Spin is proportional to helicity and also directed along the z-axis. And the amplitude intensity factor is exactly the ratio of the energy density to omega. Therefore, its energy is quantized h bar omega. We derive these quantum mechanical standard equations for the momentum and spin of one photon. Okay, but for structured waves, we can have arbitrary phase gradients and arbitrary polarization textures. So at every point, the momentum and spin densities can be directed anywhere in 3 dimensions. And to probe this momentum and spin density, typically we need to use small particles. Let it be electric dipole particle of negligible size, and absorbing. It's characterized by polarizability alpha, and imaginary part of alpha characterizes the absorption. And then it's very easy to calculate. The radiation pressure force and radiation torque on this particle are exactly proportional to the momentum and spin density in this point, at the point of where a particle is placed. There is also an additional gradient force proportional to the gradient of the energy density, but it's not important now. So it proves that this momentum and spin density make physical sense, and they're directly observable via probe particles. And interestingly, this result was first obtained by Ashkin and Gardon many years ago, but then they just derived expressions for the force which was proportional to this combination. But then nobody uses this canonical momentum of light. Everybody was using Poynting vector, which looks very different. And therefore, till recently, this result for the force and later derived for torque wasn't put in the context of momentum and spin properties of light. And only 2014 we found this very nice connection in our paper. Okay, so here direct experimental confirmation, optical manipulations. These are results from 2003. Again, a particle in a Bessel beam, and it was observed that the particle spins around its axis, so experiences a torque, local torque proportional to the circular polarization in this build and in this beam, and at the same time the particle orbits around the beam center due to the orbital angular momentum or azimuthal radiation pressure force. Okay. Next, it's important to know that, to emphasize that this canonical momentum density is not the Poynting vector. It can be directed to a totally different direction in a structured field. And the Poynting vector is actually the energy flux density. Energy flux density is not the momentum density of the field. If we again come back to Noether's theorem and energy momentum tensor in field theory, it has this form. Here we have energy density, here we have momentum density vector, here we have energy flux vector, and these two vectors are different in the general case. And here we have stress tensor, which is momentum flux density. So the energy flux density enters the energy conservation law, but momentum density enters different momentum conservation law. So this was noticed in particular by Belenfant and Rosenfeld in the context of relativistic field theory for relativistic quantum particles. And then they found some relation between this energy flux density and momentum density, which can be written in modern terms like this. So Poynting vector divided by c squared is equal to the momentum density of the field plus half of the curl of the spin density. So Poynting vector includes both momentum and curl of the spin. And this second term, we can call it a virtual spin momentum. Why virtual? Here I explain its origin. Let's assume we have some inhomogeneous polarization texture. Red and blue colors correspond to right hand and left hand polarization. So spin is directed out of the plane. It's positive here, it's negative here. So we have a spin gradient. And now if we calculate, sum up currents from these small loops, like local momenta, local motions from these small loops, we can see that they don't exactly cancel each other. If the spin would be homogeneous, we would have homogeneous polarization distribution, the same ellipses. They would cancel each other in every point, right? I mean, linear motions. But here they don't. And this current, which appears due to this non-compensation, is exactly 1/2 of the curl of the spin. So actually, nothing is transported. There is no global motion. There is no transport. But locally, you can see current. It's exactly similar to the magnetization current in condensed matter. When you have inhomogeneous magnetization of the material, your curl of magnetization gives you this magnetization current. Oops. Here is a nice example from classical field theory textbook by Soper. Imagine that you have like lattice of streets, like in Manhattan, and you have building blocks, and you have cars going around buildings. There is no linear motion of the cars. They just go around every building. But if you have more cars going here than in the next block, at the street you will see the net current, right? Because 3 cars goes down, 2 cars goes up. But actually there is no global transport. It's just an artifact of local observation, right? Okay. The next system we consider is sound waves. And as we know, sound waves are longitudinal waves, but what is important, these are vector waves. For example, this is a plain sound wave in a gas or fluid, and we see that molecules of this gas moving forward and backward. So displacement of the medium particle is our vector field, capital R. We can introduce also scalar pressure field, which is given by divergence of R, and vector velocity field, which is given by time derivative of R, obviously. So this R is a vector potential for the velocity, we can say. And now polarization of the field R is just the real space trajectory of the particle in the air or fluid or any gas. Okay, so the field Lagrangian can be written like this. Again, the similar form with the kinetic energy, which is really the kinetic energy of the particles, and potential term due to the pressure. Beta is compressibility coefficient, and this is speed of sound instead of speed of light. Since the Lagrangian has universal form, we can use universal equations for momentum and spin density. Very similar to electromagnetic, now just different coefficients, and the vector field R displacement instead of electric field. Okay. So in contrast to plain electromagnetic waves, which has spin and momentum, plain sound wave has no spin because we have only just longitudinal linear polarization, and so no rotation of the field, and that's why we say that phonons are spin zero particles. But if we consider superposition of multiple waves or structured wave field, then we can have any momentum distribution, any phase distribution, and any polarization ellipse distribution in sound waves and interfering sound waves. The simplest example is provided by superposition of 2 plane waves. So first, let's consider superposition of 2 transverse plane waves, like electromagnetic waves, and we can see that this generates a periodic texture of all possible elliptical polarizations on plane. And now if we consider superposition of similar longitudinal waves, like sound waves, we see almost the same distribution of polarization ellipses. All possible ellipses just periodically distributed in the transverse direction. You can verify it by simple calculation of superposition of 2 waves. You can see that the field along x and y direction have this I coefficient, and it's periodically dependent on y. So we have z-dependent spin, and momentum density is x-dependent along the mean wave vector. Okay. Now we can measure acoustic spin and momentum density in the same way as in optics. We take a small particle, absorbing particle, let it be dipole particle, which induces acoustic dipole proportional to the velocity field and characterized by polarizability alpha. Then the expressions for the radiation pressure force and torque are exactly the same as in optics. And we found the first expression for acoustic forces was found by Garykov, but in this form, we calculated them only in 2019. And there is also gradient force, also similar to optics. Okay, so acoustic spin is a kind of interesting story. Again, we found a very nice, like a milestone paper from 1973 in Journal of Fluid Mechanics by Jones. And until 2022, it had less than 10 citations. Actually, this is, to the best of my knowledge, is the first paper which introduced acoustic spin. But it was totally neglected because for everybody, sound waves were spinless. Nobody believed in sound wave spin. But Jones derived it from also field theory and asymmetric energy momentum tensor, all rigorous derivation, and found exactly the same expression as I showed before. And he noticed a very clear physical meaning of this expression. Is simply the cross product of the particle displacement and particle velocity. So it's really mechanical angular momentum of particle making an elliptical trajectory. And this local trajectory due to wave field, exactly the spin angular momentum, generates spin angular momentum. Okay? And the modern wave of interest to acoustic spin started in 2019 with this paper from a group by Ji Ren from China, and they made an experiment interfering two sound waves and placing resonant absorbing structure. They called it the acoustic meta-atom, which absorbs sounds and experiences torque from these two interfering waves. And torque exactly measured the spin distribution picture. Okay, so the spin density makes a clear physical sense. What about momentum density in sound waves? And here we need to notice that sound and any mechanical waves are inherently nonlinear. Why? Because the wave field displacement happens in real space. So the particle is displaced by the field, and then it experiences the action of the field not in the original point, but in the displaced point. And this produces a nonlinear response. So for example, let's write an equation of motion for one particle. It's density, mass density, multiplied by derivative of velocity is equal to some force I just denoted by letter G. But this force should be taken not in the original coordinate of the particle, but in the displaced coordinate, plus r. Again, making Taylor expansion, we obtain quadratic term in the field. And using perturbation theory, we calculate average contribution of this quadratic term to the force or acceleration of the particle. And we see that the force is, we have this gradient of kinetic energy term. It's gradient force, ponderamotive force. And we have time derivative of this combination, which should be some sort of momentum. And this momentum is exactly the canonical momentum of the wave. And it's exactly the phenomenon known as Stokes drift, which I showed in the beginning. So canonical momentum of the sound wave is just mass density multiplied by the Stokes drift of the medium particles. So here is the actual picture how particles move in a superposition of two plane waves. In addition to these elliptical oscillations, they experience Stokes drift, which is exactly what produces canonical momentum density. Okay. So in contrast to electromagnetic waves, where we can debate what we call momentum, what we call spin, it's not what we can observe with our eyes, right? It's a kind of theoretical concept. Here, it's directly observable in all mechanical waves, sound waves, or water waves. It's directly observable quantities. So local rotational motions of the particles generate spin, and Stokes drift of the particles generate momentum density. Again, similar to optics, there is energy flux density, acoustic analog of the Poynting vector. The Belenfant-Rosenfeld relation holds true. It has the same physical meaning, so the energy flux is canonical momentum plus 1/2 of the curl of spin. And interestingly, energy flux density, the acoustic analog of the Poynting vector, was derived by Umov 10 years before Poynting. Another paper published in the wrong place, again in Russian Empire, but now in Odessa University, which is now Ukraine. And we found this scanned copy of the original paper. It's called Equations of Motions of Energy in Bodies. And it's a very nice paper because it's the first paper which formulated the energy conservation law in modern form. This is integral of the time derivative of energy. This is letter E, which is Slavic E for energy. Time derivative of the energy density. And this is divergence of energy flux. And Umov formulated it for any wave field and calculated in particular for sound waves, elastic waves, and waves in fluids. So for example, this is energy flux for sound waves. We have a product of velocity and pressure, and this is higher order nonlinear term. So exactly the one which I showed here just before. So it's another very nice result. By the way, there is a nice remark, probably also, it's permitted by censorship. Not by referees, but by censorship. Again, a signature of Russian Empire. And finally, how many time do I have?
10 minutes.
10 minutes, okay. Let me show some examples of these things in the water waves. The first come from our collaboration with Michael Schatz's group in Australian National University, published 2022 in Science Advances. There we interfered several plane water waves in a water tank and observed motion, put some powder on the water surface, and observed motion of water surface particles with a camera, top view. So this is just a two-wave interference, which I showed before. This is a theoretically calculated distribution of the momentum density, which are black arrows, and orthogonal spin density, which is blue and red densities. This is theoretically calculated trajectories of particle motion, and this is what we observed with camera. And it's more or less exactly captures all the features of this spin and momentum or Stokes drift distributions. And if we interfere four plane waves or two orthogonal standing waves, which were pi over 2 phase shifted with respect to each other, this superposition forms a square lattice of vortices with topological charge plus minus 1, L equal plus minus 1. So this is theoretical spin and momentum density distributions, particle trajectories from calculations and from experiment. You can see that in the center of vortices we have maximum spin density. Particle just make local circles due to the wave perturbed trajectories. And there is a global orbital motion due to the Stokes drift, which describes orbital angular momentum contribution. Okay, in general, we can calculate orbital angular momentum modes for water waves. And this is a vector field, so it's given by Z displacement of water surface plus X and Y displacement in the plane. And it has a universal form involving Bessel functions of order L for the Z component and orders L plus minus 1 for right-hand and left-hand circular polarized component in plane. This is the eigenmodes of the total angular momentum operator, very similar to optical Bessel beams and so on. And you can see this solution. So for L equals 0 mode, the maximum intensity is in the center, and polarization is vertical linear. So the central particle goes up and down. For L equal 1 vortex mode, you can see that in the center there is a circular polarization. The particle goes around, along the circle. So only the Z component of the field vanishes, but X and Y components are non-zero. And only starting from L equal 2, the central particle becomes motionless. So all amplitudes vanish. Okay, these are results from our recent paper, which I showed in the beginning. This is a complex Z field phase and amplitude distributions for these vortices, and these are calculated from experiment momentum density and spin as Z component distributions in these fields. Let's go next. What's wrong with it? Okay. And we thought, an interesting result from the same paper, we thought that since water wave water waves have the same dynamical properties as optical or acoustic waves. Can we manipulate particles similar to optical and acoustic manipulations? And we just guessed that there should be usual radiation force due to the momentum density and some gradient force due to the gradient of intensity. And there should be torque proportional to the spin. So we put a particle in structured water wave field, floating particle, a small plastic particle on the water surface. And first we observed for the L equals 0 mode that the particle is attracted to the maximum intensity zone and is trapped there. So it's similar to optical trapping discovered by Ashkin. So, wait a second. So this is, I'm going to show you the movie. And please ignore this black and white checkerboard pattern because it's due to the optical setup in our experiment, how we recorded the wave field. So here is the pale particle. Let's see. We start the wave. You will see here is the wave. And the particle is attracted to the center and trapped there. Now, if we use L equal 2 vortex, we see that particle is trapped in the maximum intensity zone and orbits due to the orbital angular momentum or azimuthal pressure force. Let's see. Here is the particle attracted to the maximum intensity, and here it orbits according to the vortex direction. Okay. And finally, a bigger particle, which was a ping pong ball in our case, L equal 8 vortex, so the size here is 4 centimeters diameter. And in addition to the orbital motion, we observed also spinning motion of this ping pong ball, which actually corresponds to the spin density in this inner part of the maximum intensity ring. Let's see. Doesn't work too well. Okay, here it is. Yeah. So it's pretty much stable, and this is exact water wave analog of optical and acoustic manipulations first suggested more than 20 years ago for vortex beams. Okay. So in conclusions, I introduced this concept of momentum, spin, and orbital angular momentum for different waves, provided field theory approach how to calculate these quantities in a universal way, showed that this works very well for electromagnetic waves, sound waves, and can be nicely visualized in water waves, and showed water wave manipulation of particles. And I would like to remark that such approach can be applied also to condensed matter modes, such as spin waves in ferromagnets. A couple of months ago, there was 2 preprints from the same group in France with a very similar approach to angular momentum and field theory for spin waves. Okay, thank you very much. Do I have a couple more minutes or no?
Yes, no problem. You've kept the time very well.
Yeah, if you would like to ask questions, you can ask, because I wanted to show just a couple of minutes some recent result, which could be interesting to the audience. But if you would like to interrupt me and ask any questions, you can do this. No? Should I proceed? Okay, so I would like to acknowledge this conference and SPICE, because exactly 1 year ago I was here and I met Elisa De Ranieri, chief editor of a new journal, Newton, here in this audience. And this journal started in January, and it's supposed to be a flagman journal in physics from Cell Press. So we wrote a commentary with Mark Dennis celebrating 50 years since the pioneering paper of John Nye and Michael Berry introducing phase singularities. And also, like months ago, we published our recent results in collaboration with DAPC teams. And here is the main idea. So as I mentioned, in a 2-dimensional wave system, we can have wave vortices and standard formulas given by these Bessel modes. And you can notice that the size of the energy confinement in such vortex cannot be smaller than the wavelengths. So the minimal radius of the minimum diameter of the L equal 1 vortex is the wavelength. And the higher is L, the larger is the radius. And this is a kind of problem, because if you would like to confine energy with vortex to smaller scale, you cannot do it. So example of wave vortices can be found in ocean tidal maps. as was mentioned by one of yesterday's speakers. So here is phase and amplitude of ocean tides, and you can see many zeros intensity and phase vortex points called amphidromic points. For example, this amphidromic point in the middle of Pacific Ocean, if we compare with the Bessel beam solution, it fits very nicely. And the wavelength is about 10,000 kilometers for ocean tides. Now, and you can generate the same Bessel modes, for example, in surface plasmon polaritons. It's a 2006 result. Bessel modes of different orders generated in surface plasmon. Anyway, and now we had an idea that there can be different type of vortices, which we call type 2 vortices. Because usual vortex, type 1 vortex, it behaves like proportional to R amplitude, so it vanishes in the center. But there can be solutions of wave equation which behave as 1 over R, and which diverges in the center. But such solutions can be realized only in a not simply connected space with a hole in the center, because we cannot allow infinite amplitude. We need to make a hole in the space to realize such vortex. And remarkably, you can indeed write this usual Bessel solution, and the Bessel solution with type 2 Bessel function, which behaves as 1 over R near the center, if we have an exclusion, a hole in the space. And what is most remarkable, that size of this vortex can be arbitrarily small. For example, here we made the hole of the size lambda over 20 instead of lambda over 2. And you see that all the energy is confined around this hole, and we have a perfect vortex. So here, the confinement is determined by the size of the hole instead of the wavelengths. And indeed, we found such vortices on the same ocean tidal map around New Zealand and around Madagascar. You see that intensity is very bright here. Around New Zealand, there is a charge 1 vortex. And the size of this vortex is lambda over 6. So it's really a subwavelength phenomenon.
Sorry, what is the color?
Color is the phase, as usual. Yeah, so you have opposite tides on opposite sides. OK, so we provided a very simple toy model how we can generate these vortices. It's just an interference between a dipole and plane wave. And dipole has a divergence 1 over R in the center, as usual. And adjusting the amplitude and phase of the plane wave, we can control the generation of the vortex around the dipole. So, and here is the result from our model compared to the tidal waves. You can see it describes it very, very well just with 2 parameters. And the explanation could be very simple, because these huge islands of New Zealand and Madagascar, they oscillate due to the moon gravity with the same frequency. So they produce a kind of dipole source interfering with the ocean tidal wave, produces exactly the picture. And we also made experimental numerical simulations in optics for nanoholes in a plasmonic surface. So for example, you can excite a vortex by circularly polarized light, incident from the top, and you can see that this vortex, it's independent of the size of the hole. You can scale it down to any subwavelength size. The picture is the same. Actually, such vortices were observed in plasmonics, but only for the holes of the wavelength size. Nobody went really down to subwavelengths. We did experiment with Fanon polaritons and vortices around nanoholes. So I will not go into details. And this is just the picture of how real field intensity varies in time in our dipole model around New Zealand for tidal waves and around nanohole in the polaritonic surface. So it's really like a generic phenomenon, subwavelength phenomenon. OK, thank you.